Okay, welcome. Happy Columbus Day, Indigenous Peoples Day, as some people have it. Happy Canadian Thanksgiving, all today. But for us, I guess it's review time. And so I thought the most useful thing to do is to allow you to maybe focus in on what to work on. And so we'll do that today. So I think I mentioned already. If not, I haven't sent it yet on what the topics are. Maybe we'll craft out one sheet of one page of this that includes all the equations you basically need. The things that are present would be manometer equation, Bernoulli's equation, which gives you a free jet as well, and conservation of mass and of linear momentum. And that's it. And so we'll jot those things down, and then we can maybe chat around them. I don't know what to do for. If you've looked on the website, you should be able to find. If you find me, and I don't know if you all use these resources page. So right now there should be some review notes, which is what I'll use today, and so it's 20 pages or so, but we'll go through that later on today, but that's available to you. And I'll post this recorded component after the fact. So we'll have that, it'll be available, whoops, not on here, I guess it's, it'll be available where these things are. It'll be here, I guess, is where it'll be. I guess it is topics 4, 5, 6, and 7. We finished 7 last time. We didn't really cover angular conservation momentum, so that tells you something. If you want to see that for your own edification or for doing the assignments, you can certainly find it here. It's from last year. And so we kind of ran out of time, but I thought it was more useful to do the things that we did last time with 7.3 than to dilute it by talking about rotational momentum. So that tells you something as well in what you might review in preparing for this. Okay. So yeah. So why don't we go back to this and just jot down the things that you already know, but it's always useful maybe to review. Manometer equations. I mean, I think we'll go through this, but you remember the rules, right? If you go up, you subtract pressures, and I guess we get pressures by pressure changes are equal to unit weight of the fluid times the heights. So if you go up, you subtract. If you go down, you add. What else? You don't need this, but if it's evacuated, then you need vapor pressure. And there's one other. I guess the other one is if it's a gas, then the unit weight of the gas basically goes to 0 when you use this. So the pressures everywhere is the same. Because the difference between the density of a gas and a liquid is a factor of 1,000, then typically it's a tiny increment. Okay. Bernoulli. We know Bernoulli in 2 forms. One is parallel to flow. And so if we have a streamline, it's always the velocity on the streamline that we measure typically between 2 points. We can also get the changes normal to that streamline, which we'll talk about. But as we know, write it any way you want. I always write it this way. Elevation plus pressure head, all in units of length, plus velocity head is constant along the length. So what we typically do, as you know, and you've done many times, is we write it between 2 locations and hope that we have enough to be able to solve for only one unknown. If we don't, if we have more than one unknown, then often we would do something like conservation of mass, which we now know in a much more sophisticated way, but basically V1A1 is equal to V2A2. And of course that refers to the fact that we have a stream tube, that we have areas upstream and downstream. And you know that. The velocities are always in the direction of the streamline. That's the maximum direction. So when we start talking about things normal to the streamline, of course, there's no velocity in that direction. So the velocity that you'd want to use would be, let me do this, that you'd want to use would be in that, the velocity would be along the streamline, but it's the pressure that you look at as you tracked across here. Typically, by convention, we always write upstream and downstream. It doesn't matter in the stuff we've done so far because we don't have any frictional losses, which will get added in here. Ultimately, we'll find that we can put head losses in here, and then it does matter whether it's upstream or downstream, but for now, that doesn't matter. Is there anything else we need to know? It's useful, I guess, to think about this in terms of, okay, in terms of, we've drawn this diagram before, I think. We've drawn this diagram before, I think. We've talked about a hydraulic grade line and an energy grade line. And I guess the EGL would be all of this. This isn't something you need for the test, but it's something that's useful for us to think about. And the hydraulic grade line are these two components here. And because this is constant throughout, then if we drew the hydraulic grade, the energy grade line, it would look something like this, right? And it's useful because we know, for instance, the big tank assumption, velocity equals 0, and therefore this, I actually choose a point, this is probably a more interesting point here. This point here is going to be P1 over unit weight. And if this is z equals 0, then this will just be elevation z1. Velocity is 0 at the top. If we had that point here, then this would be now z2. The pressure now is not going to be 0 anymore, and also the velocity is not going to be 0. And so we don't know exactly what those components would be. It's not necessarily the top of this pipe, but this amount here would be V2 squared over 2g. And this amount here would be pressure 2 over unit weight. And I presume that when we get here, the portion that's going to be the velocity head, we could imagine is now going to be larger, because all of a sudden it's being constricted, right? So we know that V2A2 is equal to V3A3. And so if A3 is smaller than A2, then it has to speed up to correspond. So that's our pictorial representation of it, and you all know that. Bernoulli perpendicular, which you actually don't need, but don't switch off, is something, if we write it in the same terminology as before, it's equal to elevation, z1 plus P1 over unit weight. And I write it this way just to be consistent with what's above. 1 over gravity times velocity squared over the radius of curvature dn, and there's an integral in there, is equal to z2, etc. Same term. This is 1, by the way. And the terminology for that, if you recall, is that this is the radius of curvature to that streamline. N is the direction pointing into that center of curvature. Z is always, in everything we've done, vertically upwards. And so the increment of dn in the same direction, it just becomes that, in this particular case, that dn is equivalent to dz, if this is vertical. And so if you know the radius of curvature, you know the streamline velocity, this would be vs. And if you know this, then basically what it does is it gives you a magnitude of a centripetal force. And so one way to think about this, just again for your own edification, is really what it's doing. These two terms together, this is how pressure would change as you go here. So if this is positive, this will still be positive. And if r is not infinite, if it's infinite, it's just a straight flat line and there's no centripetal effect, then this basically would increase the pressure as you go down here. So if you're looking at a beaker of water, and if you're looking at the pressure change with depth as you go down here, then normally it would be, pressure change would be equal to rho gh, or rho gz, I guess, if z is downwards. I know I'm violating my own rule of having it upwards. But if you're going around a turn like this, basically it would make it larger by some amount. And that some amount would be this physical term that you're just adding on an extra amount of g to this. Basically you're augmenting gravity, so you'd feel more. So for sure you need Bernoulli along a streamline. I'm not sure you need Bernoulli perpendicular to a streamline. I guess the other thing is free jet. Doesn't matter whether it's coming out of the bottom of the tank or the top. But if this is some height, then you know that the velocity is equal to square root 2gh. And you don't need me to tell you that. You can just do Bernoulli between 2 points, and you know that this is atmospheric, has velocity, and you know the elevation. This is atmospheric, has zero velocity, if it's the big tank assumption. And as a result of that, you just get this out of applying simple application of Bernoulli. Okay. Everyone good so far? All right, so that's the first part. And there are only two other equations to deal with. One for conservation of mass and one for conservation of linear momentum. So what's our shorthand for conservation of mass, I guess? We've written it in a couple of different ways, but the easiest way to write it is that density multiplied by a rate of change of volume plus a volume times a rate of change of density plus, we've written it, I'll write it this way first, sum of all the inputs and output of the system, I guess, would be density of velocity across the control surface times an area is equal to 0. This, I guess, on occasion we've called mass flow rates, or sum of mass flow rates, and that's it. I guess it's useful also to remember our version of the SS Titanic. Squirting water out at some velocity W. A motion of this velocity of the control volume. Velocity, not volume. And this is my eye. Can't draw an eye very well. But this is the velocity relative to a static observer. And so we know that V static is equal to the velocity of water squeezing out of the pipe plus the velocity of the control volume. These are vectors typically, but often we can think of them just by resolving in one direction, in x, say. So you can probably get away with using, you won't need to use this in its integral form. This is a dot product and a differential area, but you should be, you certainly can use it. Remember we did one in class, or you might remember in class we did this block with a jet coming out of the side of it. What force you had to apply to clamp it, and the jet varied with, the velocity varied with the distance away from the end of the block. But I guess you do need to know the sign convention for this, right? So the sign convention is always out is positive, in is negative. Increasing, so density increasing with time is positive, and volume, anything increasing with time would be positive. So those are the, I guess there are those three sign conventions. Increasing with time, density or volume are positive. Flow out is positive, and therefore the opposite of that is negative flow in. So if you have that, then you're fine. Okay, all right. And conservation of linear momentum. And the expression, the worst expression you need for that, or the uppermost expression, I guess, is velocity plus velocity of the control volume. I guess we don't put a line through these. Multiplied by a mass flow rate is equal to the sum of the forces. I don't know what so forces in x and in z would be typed relative to the global coordinate system, always. And so a velocity static in x would be in this direction, in z would be in this direction. And these are really vectors also. But if we want to just resolve in one direction, which we might do, then it would be relative velocity in x plus control volume velocity in x times mass flow rate, which is a scalar, is equal to all the sum of the forces in x. What else? Just as in conservation of mass, the sign convention is positive out of the control volume, negative if in. But for both W and velocities, all of these are positive in the coordinate direction. In global coordinates. So in other words, this time. The forces are the forces that have to be applied to keep the thing in equilibrium, to be doing what it's doing. So equilibrium might be that the velocity is not moving, so you have to hold it in place with these forces to do that. If you describe these, in the proper coordinate direction, and it comes out negative, it just means that the actual force is pointing in the opposite direction to keep it static. And you'll recall that the way that we use these forces are in three modalities. The modalities is, what do we call it? Call it anchored. We call it something else other than anchored. So we can call it anchored. In other words, the velocity of the control volume is equal to 0, and the forces are not equal to 0. In other words, you have to apply a force. If you're shooting a jet at my chest, then for me to stand still, I have to be applying a force against that destruction of momentum. Freely moving, I guess. I'm leaving a space between these. And so that would be that the force is equal to 0, and the velocity of the control volume is not equal to 0. And the other one could be a prescribed velocity. Velocity of the control volume or a prescribed force. Right? Just partway between them. So these are very specifically prescribed velocities. These are very specifically prescribed forces, but we could prescribe a force which was 10 newtons instead of 0. And in that case, it might have a velocity, but it would also have a force attached to it. And so, and again, in these, the same, exactly the same sign convention applies that we've used here for conservation of mass. Oops, that's all you need to remember. So there's no expression that you need other than these 2 pages. So you can guess what do you need. Remember, so I don't know. I'm happy to take questions. I'm happy to go through the rest of the material as people wish. As I say, the questions, manometers is kind of slightly out of this, right? It's maybe in section 3 or section 2 we did manometers, but it's you need that to combine with this to solve some of the questions. You can probably guess that combining that with Bernoulli is something that we've used in the past, and we can look at actually a quick example as we go through this now, if you wish. Yes?
So what videos have been covered? Just from like after the first midterm to like describe
It is 4.2 through to 7.3. So 4.1, if you remember, was accelerations, right? Yeah. And so it's really Bernoulli, which started on 4.2. So 4 and 5 were Bernoulli, 6 was conservation of mass, and 7 is conservation of linear and rotational momentum. And so you can throw. So, all right. Anything else? So I could say other things, I guess, but do you want to quickly go through this? I'll make some comments about different questions. Maybe look at the previous. I don't know if you look at the previous review session, the recording of it, whether you can make any correlation between the length of time that we spend on talking about things within that evening relative to what might have turned up on the test or not. But I think you can play those games. I don't know if that happens subliminally to me or not. But So we know that we don't need all of these, but we've talked about the ones. We've said that, I didn't say, but I didn't include rotational momentum in what we talked about, and so you can resign that to the dustbin of posterity if you wish, or not. It's up to you. So, manometer equations. I think that was new 5 or 6 weeks ago. I think you know how to do that now. Is you move up and down in static fluid. It changes pressure by a magnitude equal to the height change times unit weight, and it matters whether the fluid is a gauge fluid or the fluid that you're dealing with, but it's just static equations. If you're dealing with flow into the page, then you're dealing here with a pressure at these points, and so Bernoulli or velocities never enter into this. It's just a straight moving from one location. You start off with pressure A, and you add to it the change to get to this point. You go across in the same fluid to the same location. You know it's the same pressure, and then you add this portion to it, and you end up with, after all the terms, is equal to P4. You figure out what you know. So if you know this is atmospheric, then you can solve for whatever you want. And it's probably, in this particular case, the pressure at A. So you need to remember that. So you remember that when you go down, we've already said it, you increase pressures. When you go up, you subtract pressures. Vapor pressure if it's an evacuated closed volume, and unit weight of gases are basically zero compared to liquids. So I've said that. We talked a little bit about streamlines on a curve. We've talked about that enough. We talked about Bernoulli in this intrinsic form. We wrote it slightly differently, but that's basically the same equation we had before, written just at the bottom of this page, so no different. And certainly you know how to deal with that. You know the code words, right? A large tank means velocity is zero on that surface where you write it. We know that if you're destroying velocity at this point here, then you build a pressure change due to that. You know that you can get the equation for a free jet by applying Bernoulli. A large tank, therefore, the velocity is zero. We know what Z1 is. We know that the pressure is atmospheric. If we're doing all of our calculations relative to atmospheric pressure, then atmospheric pressure is zero. We know at this other point here that the pressure acting outside this tank is also atmospheric, and so pressure at a point is uniform in all directions, so therefore this has to be atmospheric. The velocity is not equal to zero. That's what we want to solve for, and we know the elevation at this point. And so in this particular case we can solve Bernoulli because we have only one unknown. The unknown is V2, and we end up with the equation for a free jet, which is this here, which you can do in your sleep, I think, just by looking at those components. If you take the jet as it goes down here and keep on looking at it, you could calculate the velocity at this point. If you did that, as we talked about in class, you'd find out it's no different than me dropping this pen. It accelerates at the acceleration due to gravity. It's like dropping a ball on the floor, and its velocity would be increasing just as if you dropped something that originally had a velocity v2 that you are throwing at v2 at this point, and its velocity at any portion down would be increasing because of gravity. Physically, I guess we'd know that because that's happening, if it's going faster at v3, if v3 is greater than v2, then we know that from conservation of mass, if v3 is larger than v2, then a3 has to be slimmer, right? It has to slim down. And we messed around with that, I think, in class for a little while. So free jet, you certainly know. Okay. Went through this in class as well. Free jet as well. The essentials are, what are the essentials? The question is actually what is the height this reaches. So the essentials are, one, to figure out exactly what the velocity it comes out of this jet at V2. And so if we know that P1 is atmospheric, if we know that V1 is a big tank, and we know C1 is this, then here we know also that P2 is atmospheric. It's a bit more complicated than it needs to be, but Z2 we also know, and so the only thing we don't know is V2. If we know V2 coming out of here, then we know everything about this in terms of the velocity. And so we can divide this into a velocity both horizontally and vertically. And the two things we know about this is that if we don't change, there's no gravity acting in the horizontal direction. So the velocity of me throwing this pen across the room, if drag wasn't working on it in the air, it would go forever until, of course, it hit the ground. But it would go forever until it hit that wall, and it would still be going at the same horizontal velocity. And so if you want to calculate, you could calculate Bernoulli between points 2 and points 3. Point 2 is going to be the streamline velocity that you've calculated here. Point 3, because it's traveling at this horizontal velocity, v2x, it'll still be traveling at that same horizontal velocity here, and it'll be traveling at that same horizontal velocity here just as it hits the ground. And so if you write Bernoulli's equation for point 3, by definition, the velocity at that point has to be v2x. And we know what v2x is if we know the inclination of this. And so you could write Bernoulli between points 2 and 3. The only unknown is z3. And that gives you the height of rise. And so that's the rationale. So, half the deal with these problems is figuring out what it is you're being asked to solve for. And so in that particular case, it's just making that connection. Okay. Confined flows, conservation of mass in its simplest form. We've mentioned a number of times. In Bernoulli, we do that if we have two unknowns in our equation. Then typically we can write V1 A1 is equal to V2 A2. And depending on which one we want to write, we end up with V2 as just being the ratio of A1 over A2 multiplied by V1. And so if you substitute this into Bernoulli, I guess as squared, then you can eliminate one of the variables. And you know how to do that. Some big pictures, what did we say? Sometimes you can't always, don't always want to make the assumption that big tank is a big tank. And if you don't make that assumption, then what you have to do is you have to say that this has some velocity, v1. And if you do that between points 1 and 2, you aren't necessarily able to eliminate that magnitude except by using conservation of mass principle. So this is continuity. And so it turns out that if the tank is quite a small tank, then the solution does get controlled by V1. It does have some influence on it. And you can't use the free jet expression that V is equal to 2gh. Because this implicitly is assumed that V1 is equal to 0. And so I'm not sure we spent much time on that, but just an observation that might be helpful in a broad sense. Manometry, that's why I mentioned that you should look up manometry. Look through the prior exams, you'd often see something like this. And the idea is that one, you need to put the velocity at this point to be 0 because it's being killed by a stagnation point. So V1 equals 0, which I guess is this right here. And V2 is not equal to 0. So for instance, you could write Bernoulli between these 2 points, as it's written here. And typically, what a manometer is measuring is measuring a pressure difference between these two locations. So long as you can write Bernoulli in terms of the pressure differential, not the absolute pressure, but the pressure differential, P1 and P2 will both be there. Would be equal to what? In this case, it's going to be Z2 minus Z1, which I think is 0, right, between these points. And it's going to be plus P2 over gamma minus P1 over gamma. Oh, no, what am I talking about? It's going to be V2 squared over 2G minus, whoops, V1 squared over 2G. And so this is what you want. And this, of course, is what the manometer equation gives you, is the difference between two pressures at these particular locations. So this you can probably get from the manometer equation, which you can see right down here, I think. And in this particular example, these are 0, difference between these because they're on the same physical horizontal plane. And these maybe you could link between V2 A2 is equal to V1 A1. And so you can write this only as one velocity and solve it. So in the cases where you don't think you have enough equations to be able to solve it, the manometer part gives you differential in pressures. Doesn't matter if it's a 1,000 kilonewtons, 1,000 kPa and 1,001, or 1 kPa and 0 kPa. It's just the differential that makes the difference. And so you find out that you just need this. So that's the typical way in using manometers. And you have to be sure to write this in an appropriate way. Free jet, what's this doing? Someone asked this at a previous review session, there will be no need to do any integrations. This is just, we know that Bernoulli is a steady state representation of things, and but yeah, you don't need to do any integration such as this. Control volumes, we talked about different kinds of control volumes, static, moving, non-deforming, and deforming. We went through some examples. I don't think you need anything quite as elegant as the ones we used. I'm trying to look to see if there's some examples here we can use. Yeah, you don't need. I don't think you need anything very complicated for conservation of mass in terms of moving control volumes. But anyway, this is the relationship we talked about before. We talked about lots of moving control volumes and defined in terms of velocity is equal to relative to the hose man, woman, plus the velocity of the control volume, which is these equations here. But I don't think there's anything so sophisticated in terms of conservation of mass. You certainly do need V1A1 is equal to V2A2, which we talked in the context of Bernoulli. And we've got 10 minutes, so I'm trying to think. Yeah, right. And in terms of conservation of momentum, we spent, I think there are probably 2 examples here worthwhile looking at. Yeah, spend the rest of the time on these 2 examples mainly, and talk about what might be important in defining. So we made the point before that we're talking about balancing, and I can write it up here, velocities plus velocities of control volumes in some coordinate direction, maybe x in this particular case, a mass flow rate is equal to sum of forces in the x direction. And so in this particular case, what's going on? This is equal to 0 because it's not moving. So it's the relative velocity across the control surfaces. The mass flow rate in this particular case is this multiplied through by the area. And we need to remember the sign convention. Mass flow rate. In is negative, out is positive, and the mass flow rate for W is positive in global coordinates, GC I'll just write, and yeah, I guess that's a negative in, yeah, it's positive in the direction of the global coordinates. So in this particular case, if you take X as being in this direction, then the term that represents the mass flow rate, which is this dot product here, is going to be negative, right? Because it's going into the control volume. The control volume is this section here. The velocity for the second part, in other words, this part here, is in the positive x direction. So this is negative multiplied by a positive, so it remains negative. So you have to remember the sign convention. There's a pressure acting on here. So there'll be a force due to this pressure. And so the pressure multiplied by the area here is going to be a force. And I'll just zip down to here. So there'll be a force that's applied to this. So if we're summing up these components, this would be negative here. This would be this term. The amount coming out, the velocity out is positive. So the mass flow rate is positive, but it's in the negative x direction because it's going from to the left, my left, I guess it's your left as well. And so this term here has the appropriate sign convention. It stays, it's positive here, but it's negative here. Yeah.
I see why those are forces on there, but why are those positive? One faces out, one goes in.
These ones here.
Well, I see why FAS is negative, but the P1A1 and P2A2.
Oh, because P1 is, so if you cut this off here, P1 is the pressure that's acting on this control volume in the direction of this. And likewise, P2 is outside here acting on this control volume. So it's acting on, I can't really blow it up. So if you look at this nozzle, P2 is outside and it's acting in this direction. And so it's in the positive direction as a result of that. Yeah. So it's outside the control volume, I guess, is the deal. So you've cut it here, and the pressure is acting here on this outside of this control volume. And so by the same token for this, as this is defined, this is a negative. This is if you define this as your positive direction, I think you're probably better off choosing a force in the z direction, x direction that looks like this, rather than this. In which case this would be positive, right? So just by the sign convention. And then you equate these. Think you don't have enough information. You have two unknowns in this equation, so you have to link mass flow rates across this section to mass flow rates here to get rid of one of the velocity terms, and you solve it. So that's the dissection, if you like, of it. So you need the fluid pressures here if it's a closed system. Here, what's the fluid pressure going to be at this point here? Atmospheric, right? And if you're using atmospheric gauge pressures in your calculations, this is 0. Take that as 0. Okay?
Are those, is that the density or is that pressure?
Which one?
For, like,
This one?
in the conservation rate, yeah.
This is density. Density times a velocity times an area. So this is a mass flow rate, Q.
I'm talking about the first equation, the conservation of momentum.
This one?
Yeah.
These are velocities. This is density. Density also, yeah.
And then when you say equals, is that density area?
So
On the floor that
This is density. This is density. This is density and velocity is flow rate. This is a pressure,
Oh.
and this is a pressure. So everything on the right-hand side of this are the sum of the forces. And so pressure times an area is a force, and a force is a force. So, and these are velocities times mass flow rates. The mass flow rate is this term here, m dot, and the pre-multiplier here is this. Okay. So, and so finally, this one. We spent a decent amount of time messing around with some simple views of this last time in 7.3. It might be worthwhile looking at that. Again, we can use the same expressions as we talked about last time to be able to solve this. It's done here in terms of being able to look both at the influent velocity. So this is the static velocity due to a static observer. It's a hose, static, water's coming out of it, some velocity. That's what you'd view as a velocity if you're just sitting there. It hits this vein, and it gets scooted up here, and it comes out of here. Depending on the inclination of this vein, we can take the outflowing velocity and resolve it into the two components. And so if we know what W1 is coming in here, the relative velocity, then we'd know what the W streamline, let's call it W2, has to be equal to W1 by definition. It's in the streamline direction, and so it has components that are in X and Y. And from what we said about this system, probably the only one that's going to be relevant to us is that we said that the relative velocity plus the velocity of the control volume multiplied by mass flow rate is equal to the sum of the forces. If we just resolve it, say, in the X direction, equals sum of the forces. Well, sum of the forces in X direction. And so, remember we made this point about these two end member states. Either we can assume clamped, in which case the velocity of the control volume is equal to 0, in which case you get rid of this term here, or free, in which we assume that the forces applied to it are equal to 0. And of course, for each of these kind of end-member behaviors, our interest is in being able to calculate the opposite. So we'd like to be able to calculate what forces we have to apply to keep it in place, or we'd like to calculate what the velocities of the control volume are. And so we resolve forces to be able to do that in some reasonable way. And so we spent a fair bit of time talking about these different states, I think, last period. And I think that would be a useful thing to review, just juggling between those. And we've got a minute to go. Let's see. We didn't cover this. It's on the syllabus. You might want to look at it, but I know you won't.
I mean, is it on the test?
Yeah, sure, it's on the test. No, it's not on the test. It is not on the test. So that's it. So I would say look at previous examples, look at the things, interpret what we've done here in your own particular way. Maybe look at the previous review and see how that compared with what was on the test. And I think, yeah, fine. All right, looks like a great day outside. Enjoy the rest of the day.